So we're gonna finish up the slides today, and I've pulled back up these three questions with which we started. So we've now answered all three. We talked about how fast molecules are moving, and for that we defined a mean velocity, molecular velocity, or mean molecular speed from the Maxwell-Boltzmann distribution, and then we did this kind of conceptual derivation for the root mean square speed of the molecules. Here again are some example Maxwell-Boltzmann distributions for different kinds of gases. It's important as temperature increases, the mean speed and spread of the distribution increase. Conversely, when the molecular mass increases, the mean speed and its spread decrease. We talked about how far molecules travel before colliding. We defined this value, the mean free path, which was lambda. It's inversely proportional to the diameter of our gas molecules and their number concentration. If we plug in using the ideal gas law for that number concentration of gas molecules, then we find two important thermodynamic dependencies that as the temperature increases, so does the mean free path. The gas molecules can travel further in a warm gas. And as the pressure increases and the mean free path decreases, we can kind of think of a crowded room. As the room gets more crowded, there's more pressure, then it gets harder to traverse the room. It's more likely that we will collide with somebody. And then this last question, how effectively do gas molecules transfer momentum? We define two material properties, which are viscosity and diffusivity. Viscosity answers the question, how much does the fluid resist flow? And diffusivity answers the question, how readily does the fluid diffuse? And we'll talk about both of these in more detail as we talk about aerosol motion and aerosol processes. So we have more complicated formulae for both of these properties, but we don't need to keep those in mind. We need only know that for gases, viscosity will increase as the temperature increases. That is counterintuitive or counter to our intuition from liquids. Diffusivity will also increase as temperature increases and decrease as pressure increases. So it's important to know these kind of thermodynamic dependencies. So to wrap up, we have two practice problems on gases, and I ask you please to pause the video and give each one an attempt before I talk through the solutions. So I'll give you a chance to pause now. And if you have come back, then I'm going to talk through the solution. In our first problem, we need to determine the number of molecular impacts per second on the surface of a 0.5 micron diameter particle. And this is in air at 300 Celsius. We have the gas number concentration at standard conditions. Standard conditions will come up throughout the course. And when I say standard conditions, I mean about 20 degrees Celsius, which is a typical surface temperature on Earth, and surface pressure, which is 100 or 1,000 hectopascals at the surface of the Earth. So to start, we need to adjust this number concentration of gas molecules that we have because we are looking at a different temperature. And so we can adjust that number concentration of the gas molecules with the ideal gas law. And I'd ask you, if you're not familiar with the ideal gas law, please to come to office hours and we can kind of talk through because we're going to use it as we move forward. The ideal gas law says that the conditions or the gas properties at one set of conditions should relate to the gas properties at another set of conditions. And so at a warmer temperature, then our number concentration of gas molecules decreases for an open volume. Now we can take that updated number concentration of gas molecules excuse me, I guess before we use that, we're going to calculate the mean speed of the gas molecules. And we're going to use this equation that we had earlier calculated from the mean of the Maxwell-Boltzmann distribution. An important thing here is that there are different formulations of this mean speed. We can calculate it on a molecular basis, which is this left-hand formula. This is the molecular mass in the denominator and the Boltzmann constant in the numerator. Or we can calculate it on a molar basis. And in that case, we have a molar mass in the denominator and the gas constant, macro scale gas constant in the numerator. Right, so this is the molecular formulation. This is the molar formulation. Both are equivalent. We just need to update the constant and which mass we're using. So I'll use the right-hand formula, plug in the gas constant, and our temperature and our molar mass for air, and we get the mean speed of our molecules. And now from that mean speed, this is a typo, this should be 1.27. And then from that number concentration of gas molecules and the speed of those molecules, then we get the collisions per surface area per time. So this is Z. This should be the correct value over here. And a final step then, if we just want the number of molecular impacts per second and not per surface area, is that we need to multiply by the surface area of the aerosol particle. And so we take that collision rate that we calculated and multiply it by 4 pi r squared, which is the surface area of the aerosol particle. The radius, right, is diameter 0.25 times 10 to the minus 6 meters. And we should get a collision count of 10 to the 15 per second, which I will point out the magnitude of this value. That is a huge number, 10 to the 15 collisions per second, really a lot. So the aerosol particle is being bombarded. So we have one more problem. And again, I'd ask you to attempt this on your own. You can pause the video and then come back for the solution. Okay, so if you've come back, this problem has to do with the mean free path of air at standard conditions. And you see those standard conditions again that I mentioned in the first problem. So you have a collision diameter of air, and then we want to look at how the mean free path in air changes if we increase the pressure or increase the temperature. So the first thing that we want to do is, from standard conditions, P and T, calculate our number concentration of gas molecules. This is, again, the ideal gas law. So we get 2.5 times 10 to the 25 molecules per cubic meter. We can then take that formula that we derived earlier for the mean free path, plug in the number concentration for gas molecules, and their collision diameter. We should get a value of 0.066 microns. So this is an important value to keep in mind. We will use this value a lot. If you keep kind of a sheet of constants, then I would write this down. This is the mean free path of air at standard conditions. So this is relevant a lot, right? We care about how aerosol are moving close to the Earth's surface. Another reason that this is a useful value to kind of have in our pocket is that we can use the proportionalities between mean free path and between two values of mean free path and pressures and temperatures. The way that we get these two equations that you see on the slide is basically taking the ratio of two of these equations for lambda. Then we plug in for n sub g, right, over here. The Avogadro's number and the gas constant will cancel. And if we are looking at isothermal conditions, the temperatures will also cancel, and we get this ratio of pressures. If instead it's isobaric, then the pressures will cancel because they're the same in both cases, and the temperatures will remain. So basically, we've taken the ratio of two of these equations and just canceled out what is constant. And that means then we can update the mean free path for different pressures and different temperatures without having to calculate that full equation with the square root of 2 times pi in the denominator. And so we can update for pressure on the left here. This is standard conditions, which is 101 kilopascals. We're updating to 300 pascals. And as we expect, if we increase the pressure, we decrease the mean free path. The gas molecules can travel less far before a collision. And on the right then, updating for temperature. If we move from a colder temperature to a warmer temperature, then we see that the mean free path increases. So the gas molecules can travel farther in a warmer gas. And that is all that I have in regard to gases for you.